a structure the size of a football field moving faster than a rifle bullet. 16 sunrises, 16 sunsets, every single day. A crew member's face swells within hours of arrival. Fluid shifts upward toward the skull, with nowhere else in a weightless body left to settle. An alarm cuts through a module without warning. Ammonia, toxic, and freezing at minus 33 degrees Celsius, has found its way into the wrong compartment. In 2013, a helmet fills with water in the middle of a spacewalk. For several long minutes, no one outside can be entirely certain the astronaut inside is still breathing normally. 400 kilometers below, an ocean is waiting, a patch of water so remote, so far from any shipping lane or coastline, that wreckage has been sent there on purpose for decades. The outer structure groans as day turns to night, not once, 16 times every 24 hours. A surface facing the sun can reach 121 degrees Celsius. Its shaded side, only meters away, drops to minus 157. 28,000 kilometers an hour, no engine roar, no sensation of speed at all, only silence and the slow turn of a blue horizon. A small unmanned capsule lifts off from a desert launch site in 1998, carrying the very first piece of a structure that will still be occupied without a single day of interruption more than 25 years later. A fragment of debris no larger than a coin, moving fast enough to punch through aluminum like a bullet through paper. For every month spent in this environment, a human skeleton measurably loses density, bone that took decades to build, thinning in a matter of weeks. Drinking water on board begins its life as sweat, as breath condensation, and, after a demanding filtration process, as something else entirely. A slow leak in the wrong module could drain breathable air from the entire structure in a matter of minutes, a risk crews train for constantly, and one that, more than once, has become real. No brakes, no reverse gear, only fuel, careful timing, and a slow, controlled return to Earth, planned years in advance. An engineer who grew up on one side of an iron curtain, troubleshooting an electrical fault at 3 in the morning, beside an engineer who grew up on the other. None of this is fiction. 15 nations, one structure, assembled piece by piece in orbit by robotic arms and gloved human hands over more than a decade. What is this structure? Why does it never stop falling? And how, one day, does it come down? This is Quiet Science at Bedtime. If this is your kind of story, a subscribe means everything right now. Every detail in this story comes from real scientific research and observation. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. For more than 25 years, a structure larger than a football field has been circling the Earth without ever touching ground. It is the largest object human beings have ever assembled in space, built through the combined effort of 15 nations, orbiting roughly 400 kilometers above the surface. At that altitude, it completes a full circle of the planet every 93 minutes, moving at close to 8 kilometers every second. Tonight's story does not begin in orbit. It begins on the ground in the final years of the 20th century, when this entire structure was still nothing more than blueprints, budget negotiations, and a single scheduled launch date. By the late 1980s, Two space programs that had spent decades treating each other as rivals were beginning, quietly, to explore the idea of working together. The United States had been developing plans for a space station of its own, first named Freedom, for nearly a decade. By the early 1990s, the program had been redesigned so many times that estimates place its total cost near $40 billion, with no hardware yet in orbit to show for it. In June of 1993, a vote in the United States Congress to cancel the Freedom program outright failed by a single vote. The station survived that day, but its design and its future remained deeply uncertain. The eventual merger of the two programs was never purely a matter of science. Following the collapse of the Soviet Union, thousands of Russian rocket engineers and missile specialists faced sudden unemployment, and Western governments were openly concerned that some of that expertise might be sold to nations attempting to build weapons programs of their own. Funding the Russian side of the new station gave that workforce a reason to keep building rockets for orbit rather than for anyone else. At the same time, on the other side of a rapidly dissolving Cold War, Russia possessed something the American program did not: nearly 3 decades of continuous, practical experience keeping human beings alive in space, gathered aboard a series of stations that culminated in a spacecraft called Mir. Mir had been launched in 1986, and by the 1990s, cosmonauts had already set records for continuous time spent in orbit that would stand for decades. That experience had not come cheaply. In 1997 alone, Mir suffered an onboard fire, and weeks later a collision with an uncrewed cargo vessel that punctured one of its modules and forced an emergency depressurization. Two very different kinds of experience about to be combined. In 1993, facing a station that America could not finish alone, and a Russian space program that, after the collapse of the Soviet Union, could no longer easily fund one either, the two nations agreed to merge their efforts. The result was planned as a single station, built from modules manufactured in different countries, launched on different rockets, and assembled entirely in orbit. It was given a name simple enough to describe exactly what it was: the International Space Station. Between 1995 and 1998, a preview of that partnership played out in a program called Shuttle Mir. In March of 1995, astronaut Norman Thagard became the first American to launch aboard a Russian rocket, beginning a 4-month stay aboard Mir. Over the following 3 years, 7 American astronauts would live aboard the Russian station in total, while the American space shuttle docked with Mir 9 separate times, delivering supplies and crew rotations. It was, in effect, a rehearsal, a chance to learn how two very different engineering cultures, with different units of measurement, different docking hardware, and different safety philosophies, might build something together without the vacuum of space exposing every miscommunication between them. That rehearsal ended on November 20th, 1998, at the Baikonur Cosmodrome in Kazakhstan, the same remote steppe launch site from which Yuri Gagarin had left Earth in 1961. Baikonur sits in an empty stretch of desert steppe, hundreds of kilometers from the nearest large city, chosen decades earlier partly for its isolation and partly for its latitude, which allows rockets launching eastward to gain a small but useful boost from the Earth's own rotation. Before dawn, a Proton rocket, standing nearly 60 meters tall and burning a highly toxic, self-igniting fuel combination that requires no external spark, lifted an unmanned module into orbit, its exhaust briefly turning the desert sky orange. The Proton rocket carrying Zarya had a complicated history of its own. Since its first flight in 1965, the Proton family had suffered dozens of launch failures, most tied to its use of hypergolic propellants, chemicals that ignite instantly and violently on contact with each other, requiring no ignition source, but demanding an unforgiving level of precision and handling. On this particular morning, the rocket performed without incident, releasing Zarya into orbit roughly 9 minutes after liftoff. The module was called Zarya, a Russian word meaning sunrise. It had been designed and built by the Khrushchev State Research and Production Space Center in Moscow, though under the terms of the new partnership, its roughly $250 million construction cost was paid for largely by the United States. Zarya weighed just over 19,000 kilograms and measured about 12.5 meters in length, with a pressurized interior volume of approximately 71 cubic meters. It carried its own solar panels, capable of generating around 3 kilowatts of electrical power, its own propulsion system with 32 engines of varying size, and its own set of batteries, since for the first several months of the station's existence, no other module would be attached to share the load. Inside, Zarya's pressurized volume was already partly filled with cargo netting, spare equipment, and fuel lines, leaving less open space than its size suggested. In the years that followed, once its steering duties were taken over by newer modules, it would settle into a much quieter role as the station's storage closet, one of the most cluttered corners of the entire structure, packed with supplies that had simply never found a better place to go. For that brief window of time, Zarya alone provided the electricity, the steering, and the communication link, keeping the fledgling structure alive. In orbit, with nothing yet connected to it, tumbling gently until its own guidance system stabilized its orientation, Zarya was, for a few weeks, the entire International Space Station. Zarya's design included 2 docking ports, one on each end, allowing future modules to attach directly to it from either direction. Engineers had also equipped it with fuel tanks large enough to later resupply the station's propulsion needs, a role it would continue to serve for years, long after more advanced modules made its original steering systems obsolete. Because no crew would occupy it for months, Zarya had been built to operate entirely on its own, with enough redundancy in its power and guidance systems to survive roughly 8 months in orbit unattended if something went wrong on the ground. Every system had a backup, and in several cases, a backup for the backup, since a repair crew was, quite literally, not yet a possibility. 2 weeks later, on December 4th, 1998, the Space Shuttle Endeavour lifted off from the Kennedy Space Center in Florida, carrying a second module in its cargo bay. This one was American-built, manufactured by Boeing at a facility in Huntsville, Alabama, cylindrical, and named simply Unity. It had been designed with 6 separate berthing ports, so that future modules could eventually be attached in almost any direction, up, down, or to either side. Endeavour's 6-person crew included Commander Robert Cabana, pilot Frederick Sturkow, and mission specialist Sergei Krikalev, a veteran Russian cosmonaut making history as the first Russian ever to launch aboard an American spacecraft. Krikalev had already lived through one of the stranger chapters in spaceflight history. Launched to Mir in 1991 as a citizen of the Soviet Union, he returned to Earth 10 months later to find that the country that had sent him no longer existed. His original mission had been scheduled to last a matter of months. Political and economic chaos following the Soviet collapse delayed his return repeatedly, extending his stay in orbit while ground teams on Earth worked through a dissolving chain of command to arrange his eventual landing. Journalists at the time sometimes referred to him, half in jest, as the last citizen of the Soviet Union, since he remained in orbit under that country's flag for months after the nation itself had formally ceased to exist. Mission specialist Nancy Curry was assigned to operate the shuttle's own 50-foot robotic arm, a role that would prove decisive within days. The crew spent 2 days chasing Zarya through orbit, closing the distance between the two spacecraft in careful, fuel-conserving stages, adjusting course with small thruster burns timed to the minute. On December 6th, Curry guided the shuttle's robotic arm out from the cargo bay, captured Zarya by a fixed grapple point, and drew it slowly toward Unity, which had already been lifted into position and attached to a docking adapter at the front of the cargo bay. This was the moment two national space programs became one physical object. In Houston, and in Moscow's own Mission Control Center outside the city, flight controllers worked in coordinated shifts around the clock, tracking telemetry from a spacecraft that for the first time in the history of either program, neither nation fully controlled on its own. Every command sent to Zarya's Russian systems had to be understood in real time by American controllers watching the same data scroll past in a different alphabet. Over the following days, astronauts Jerry Ross and James Newman conducted 3 spacewalks, totaling more than 21 hours outside the spacecraft, extravehicular activities in the language of mission control, to physically bolt Unity to Zarya and connect more than 40 electrical and data cables running between them. Each connector had to be mated by hand, inside pressurized suits that maintained roughly a third of an atmosphere, wearing gloves that reduced fingertip sensitivity to almost nothing. The suits Ross and Newman wore, known as extravehicular mobility units, were themselves self-contained spacecraft, built from more than a dozen layers of fabric and insulation. A backpack-mounted life support system supplied oxygen, removed exhaled carbon dioxide, and regulated temperature for roughly 7 hours at a stretch, with only a thin layer of fabric and metal separating each astronaut from the vacuum outside. Both men had trained for this exact sequence of bolts and cables for more than a year inside a swimming pool in Houston, large enough to submerge full-scale mock-ups of both modules, simulating weightlessness through buoyancy alone. Watching the real hardware connect precisely as rehearsed, more than one member of the ground team would later describe the moment as the quiet, almost anticlimactic end of a rivalry that had defined much of the 20th century. For families watching from viewing areas near both launch sites, the significance was harder to measure in cables and bolts. Two structures, born from opposite sides of a decades-long standoff, were now sharing a single electrical circuit, 400 kilometers above a planet that for most of both crews' lifetimes had been sharply divided in two. On December 10th, once every connection had been tested and the joined modules were fully pressurized, Commander Robert Cabana and cosmonaut Sergei Krikalev opened the hatch between Unity and the shuttle's own docking tunnel. Together, they became the first human beings ever to enter the International Space Station. They stayed only a few hours, checking instrument panels, installing equipment, breathing air that had been sealed inside an unoccupied spacecraft for nearly 3 weeks, before sealing the hatch behind them and returning to Endeavour for the flight home. Krikalev, floating between systems labeled in 2 different languages that had never before been operated as a single machine, later described the moment less as a triumph than as paperwork finally catching up to hardware. At that location, roughly 400 kilometers above the Earth, a single drop tool would not fall toward the ground below. It would simply drift away at orbital velocity, following its own path around the planet, permanently out of reach of the astronaut who had lost it. When the final cable was seated and power began flowing between the two modules for the first time, the structure that would one day grow to the size of a football field, with a mass exceeding 400,000 kilograms, consisted in its entirety of two connected cylinders a little over 15 meters long. It was dwarfed by the cargo bay that had carried half of it into orbit only days before. It was smaller at that moment than a school bus. It carried no crew, no life support beyond what its own systems required to keep from freezing, and no guarantee that the partnership behind it would hold together long enough to finish the job that had by then already cost more than any single scientific structure in human history. But it was already moving at nearly 8 kilometers a second, 400 kilometers above the Earth, completing a full circle of the planet every 90 minutes, 16 sunrises a day, for a structure that, as of that December, had existed for less than 3 weeks. Within a little more than a decade, that 15-meter pair of cylinders would grow into a structure spanning the length of an American football field, including the end zones, with solar arrays alone covering an area close to half a hectare. Its finished mass would exceed 400,000 kilograms, heavier than the Statue of Liberty, and larger by pressurized volume than a 6-bedroom house. None of that existed yet. In December of 1998, the entire station consisted of 2 unlit cylinders running on batteries and sunlight, with empty ports waiting for pieces that, in some cases, had not yet been fully built. Engineers on 2 continents had committed to finishing a structure whose complete design would ultimately require more than 40 separate assembly missions, spread across more than a decade, each one dependent on every mission that came before it succeeding without a catastrophic failure. Ground controllers in Houston and Moscow began taking turns tracking its position, watching a pair of unlit, uninhabited modules pass silently over both of their cities several times a day, a light too faint and too fast for anyone below to notice without knowing exactly where to look. Within weeks, amateur satellite trackers around the world had calculated its orbital path closely enough to predict, for their own cities, the exact minute a small moving point of reflected sunlight would cross the evening sky. It was already brighter than most stars, though almost no one outside a small community of enthusiasts yet knew to look up and find it. Zarya's thrusters would keep the young structure stable for now, nudging its orbit slightly higher every few weeks to counteract the faint drag of the outermost edge of Earth's atmosphere, still present even at that altitude. But 6,400 kilometers away, inside another Russian factory outside Moscow, a third module was already being built and tested, years behind its original schedule, delayed repeatedly by funding shortages in the aftermath of the Soviet collapse. That third module had originally been built in the early 1980s as a backup core section for Mir, then repurposed and redesigned once Mir's own core module launched successfully in 1986. For years, it sat largely unfinished in a Moscow factory, its completion delayed again and again by a funding crisis that followed the collapse of the Soviet Union, until American financial support, tied directly to the new partnership, allowed the work to resume. Originally scheduled to launch in 1997, the module had slipped more than 2 years behind its own timeline, at one point stalling so completely that American officials openly discussed building a replacement of their own in case the Russian version was never finished. It would take until the summer of 2000 for that delay to finally end. For the year and a half that followed Endeavour's departure, the two connected modules would circle the Earth entirely without a crew, monitored only by ground control, running through 16 sunrises a day for hundreds of days in a row, with no one aboard to see a single one of them. By late 1998, with Zarya and Unity already circling the Earth as a single unoccupied structure, that third module was finally approaching its own launch readiness. It would carry a name of its own, one drawn from the Russian word for star, and it would carry systems no earlier module had needed: a kitchen table, sleeping compartments, a toilet, and life support machinery built to keep a crew, not just a spacecraft, alive. It would give the growing station something two empty cylinders, however carefully bolted together, still did not have: a place for human beings to actually live. On July 12, 2000, that wait finally ended. A Proton rocket lifted off from the same Baikonur launch pad that had sent Zarya into orbit 19 months earlier, carrying a module called Zvezda, the Russian word for star. Zvezda was larger and more complex than either module already in orbit, stretching just over 13 meters in length and weighing close to 20,000 kilograms. Unlike Zarya, it had been designed from the beginning to support a permanent human crew, with two small sleeping compartments, a toilet, a treadmill, a stationary bicycle, and a kitchen area built around a table just large enough for 3 people to share a meal. Its design borrowed heavily from Mir's own core module, built by the same design bureau, using many of the same engineering principles that had already kept Russian crews alive in orbit for well over a decade. Where Zarya had been essentially a power station with a docking port, Zvezda was something closer to a small, self-contained apartment, equipped with its own life support machinery, its own guidance computers, and windows positioned specifically so a crew member floating at the dining table could look directly down at the planet below. Zvezda also carried the station's primary communication system for its first several years, including equipment that finally allowed direct voice contact between the crew and mission control across a much wider range of the station's orbit than earlier arrangements had permitted, reducing the long stretches of radio silence that had characterized communication with Zarya and Unity during the station's uncrewed years. 14 days after launch, Zvezda approached the two waiting modules using an automated Russian docking system called Curse, which guided the spacecraft together using radar without any human pilot aboard either vehicle. The system measured range, closing speed, and alignment dozens of times per second, adjusting Zvezda's thrusters in small continuous bursts to close a gap of hundreds of kilometers down to a matter of centimeters, entirely without human intervention. On July 26th, the docking mechanisms connected with a mechanical clunk transmitted through the structure, and for the first time, the station possessed everything a crew would need to actually live aboard it. It was still empty. That was about to change. Ground teams spent the following weeks preparing the newly 3-module station for its first residents. In September, the Space Shuttle Atlantis flew a cargo mission carrying more than 1,000 kilograms of supplies, tools, and equipment, along with 2 spacewalks to route additional cables and install handrails along the station's growing exterior. That mission, designated STS-106, carried a 7-person crew, including cosmonaut Yuri Malenchenko and astronaut Edward Liu, who together spent more than 6 hours outside the spacecraft, connecting nearly a kilometer of cable between Zvezda and the modules already in place, wiring that would ultimately carry both power and data throughout the growing station for decades to come. Inside, the rest of the crew loaded the station with food, clothing, and spare parts, effectively stocking a small apartment for tenants who had not yet arrived. Among the supplies delivered was the station's first stock of hygiene items, spare clothing sized for the incoming Expedition 1 crew, and a supply of tools specifically selected for repairs the ground team anticipated the first residents might need to perform on their own, without any possibility of a quick resupply if something essential turned out to be missing. By late October, everything was in place except the crew itself. On October 31st, 2000, a Soyuz rocket lifted off from Baikonur carrying 3 men, American astronaut William Shepard and Russian cosmonauts Yuri Gitsenko and Sergei Krikalev, the same Krikalev who, less than 2 years earlier, had been among the first humans ever to float through the station's empty corridors. Shepard, a former United States Navy captain who had already flown to orbit 3 times aboard the space shuttle, had spent months in Russia before the flight, studying spacecraft systems written entirely in Russian and eating meals with the same crew he would soon depend on for survival. Gitsenko, the Soyuz commander for the launch itself, had flown to Mir once before and would be responsible for the capsule's return journey months later, whenever the crew's rotation eventually ended. The Soyuz capsule that carried them, a design largely unchanged in its basic layout since the 1960s, measured just 7 meters long and provided roughly enough interior space for 3 seated adults, along with a small orbital compartment where the crew could stretch out briefly during the 2-day journey to the station. Beyond its role as transportation, it would remain docked at the station throughout their stay, serving as an emergency lifeboat capable of returning all 3 crew members to Earth within hours if conditions ever demanded it. For Krikalev, the flight marked his 4th journey to orbit, following his earlier missions to Mir and his role aboard Endeavour 2 years before. Few people alive had spent more cumulative time off the surface of the Earth, and fewer still had watched a single space station grow, piece by piece, from an empty pair of cylinders into a functioning home. Gitsenko, meanwhile, carried responsibilities of his own that extended beyond the outbound journey. As the crew's designated Soyuz commander, he would remain qualified throughout the mission to pilot the capsule back to Earth on short notice, a standing responsibility that meant at least one member of every station crew throughout the station's entire history has always remained ready to bring the others home immediately without waiting for any additional preparation. Their Soyuz capsule docked with the station on November 2nd, 2000. When the hatch opened and the 3 men drifted inside, they became the first crew in history to take up residence aboard the International Space Station, and though no one could have stated it with certainty at the time, the first of an unbroken chain of human beings who would occupy the station continuously, without a single day's gap, for more than 25 years and counting. Their stay was never intended to be permanent. Expedition 1, as their mission was designated, was built around a simple, deliberate principle. No crew would ever leave the station empty again. Shepard, Gitsenko, and Krikalev remained aboard for 136 days, until a fresh crew, arriving aboard Space Shuttle Discovery in March 2001, took over their duties in a carefully overlapped handover before the first 3 finally returned to Earth. That handover model, one crew relieving another, almost never leaving the station unoccupied even for a single orbit, would repeat itself roughly every 4 to 6 months for the next quarter century An unbroken relay stretching from 3 cautious pioneers learning to float through empty corridors to hundreds of astronauts from dozens of countries who would eventually follow them. Barely 6 weeks into that first expedition, in early December 2000, Space Shuttle Endeavour delivered the station's first full-size set of solar array wings, mounted on a truss structure called P6. Each wing unfolded to a span of more than 70 meters, tip to tip, longer than the wingspan of a Boeing 777, generating enough electricity for the first time to begin reducing the crew's dependence on Zvezda and Zarya's smaller original panels. The arrays deployed like a folded paper fan, unfurling from a tightly packed blanket only centimeters thick into a rigid structure more than a football field wide, extended and tensioned by a motorized mast unrolling at a carefully controlled speed. Engineers on the ground watched the process closely. A slight wrinkle appeared partway through one wing's extension, a minor irregularity in the folded material that required a brief pause before the array completed its unfolding safely, a small reminder of how much could still go wrong with hardware unfolding for the first time, in vacuum 400 kilometers from the nearest repair shop. Shepard, as commander, had requested a simple radio call sign for the new outpost during its early operations, Alpha. Mission Control obliged, though the name never fully replaced the station's official title in public use. Before his selection as an astronaut, Shepard had served as a U.S. Navy diver and worked with a Special Operations Unit trained in combat swimming, experience colleagues later noted that suited him well for coordinating a small, self-contained crew whose survival depended entirely on cooperation, discipline, and equipment they could not simply walk away from if something went wrong. The first days aboard were, by later standards, sparse. Water still had to be delivered largely by cargo ship rather than recycled on board. Food came primarily in vacuum-sealed pouches and cans, heated in a small oven bolted to the wall of Zvezda's dining area. Communication with the ground passed through a limited number of daily windows, rather than the continuous link later crews would come to expect. Even so, something fundamental had changed. For the first time since the earliest days of the Mir program, and for the first time ever aboard a genuinely international structure, human beings were living somewhere that was not the Earth, on a permanent, ongoing basis, with no planned end date. The crew's days followed a structured rhythm set largely by ground control, divided into blocks for scientific work, equipment maintenance, mandatory exercise, and a handful of hours reserved for meals and rest. 16 sunrises a day made morning and night meaningless as natural signals, so schedules were instead kept on Greenwich Mean Time, synchronized to clocks in Houston and Moscow rather than to any light outside the window. Sleep itself took place in small compartments, barely large enough to hold a sleeping bag, tethered loosely to a wall, so a drifting body would not bump into equipment during the night. Even fully relaxed, a sleeping crew member's arms would often float gently upward in front of them, released from the habit, built over a lifetime on Earth, of resting under gravity's constant familiar pull. To understand what living there actually meant, physically, it helps to look closely at a phenomenon that is almost always described inaccurately, the sensation crews call weightlessness. 400 kilometers above the surface, Earth's gravity has weakened only slightly from its strength at sea level to roughly 88% of its usual pull. A person aboard the station is not floating because gravity has switched off. Gravity is very much still acting on them, pulling them toward the planet exactly as it pulls on everything else in orbit. It is a common misconception worth stating plainly, since it shapes almost every intuition a listener might otherwise bring to this story. There is no boundary in low Earth orbit where gravity simply stops. A station at this altitude still experiences the vast majority of the gravitational pull it would feel on the ground. The sensation of floating comes from something else entirely. So why does everything float? The answer lies in speed, not distance. The station is not hovering above the Earth. It is falling toward it, constantly, at close to 8 kilometers every second. But the Earth's surface curves away beneath it at almost exactly the same rate that the station falls, so the station perpetually misses the ground. It falls and falls and falls, and the planet's curvature keeps pulling the horizon out from under it, just quickly enough that it never lands. This idea was first described mathematically by Isaac Newton, more than 3 centuries before any spacecraft existed, using a thought experiment involving a cannon fired from an impossibly tall mountain. Fired too slowly, the cannonball falls back to Earth in a simple arc. Fired fast enough, it falls at the same rate the ground curves away, circling the planet indefinitely, in what is, in every meaningful sense, a perpetual free fall. Newton calculated that the exact speed needed to achieve this balance at the surface of the Earth was close to 8 kilometers per second, remarkably close to the actual orbital velocity engineers would one day calculate for a station flying 400 kilometers up, more than 250 years after his thought experiment was first published. Slower than that speed, and an object spirals back down. Faster, and it eventually escapes Earth's gravity altogether, the same principle that governs everything from a tossed ball to a spacecraft leaving for another planet. The balance is not perfect, however. At 400 kilometers, the atmosphere has not entirely disappeared. A faint trace of it, thinner than the best vacuum most laboratories on Earth can produce, still exists, and it drags very slightly against the station with every orbit. Left unchecked, that drag would lower the station's altitude by several kilometers a month, eventually pulling it low enough to burn up in the denser atmosphere below. To counter this, Zvezda's own engines, and later the engines of visiting cargo spacecraft, periodically fire in short, carefully calculated bursts called reboosts, nudging the station back up to its planned altitude. Ground controllers track this slow, continuous fall as routinely as any other system aboard, treating orbital decay less as a danger and more as a predictable expense, paid in fuel at regular intervals. Astronauts and everything around them, tools, water droplets, crumbs from a meal, are all falling at exactly the same rate, at exactly the same time. Nothing appears to press against anything else, because nothing is being held up against gravity in the way a person standing on Earth's surface constantly is. The condition has a more precise name among engineers than weightlessness: microgravity, a state of continuous, shared freefall. This single fact explains far more about daily life aboard the station than most people expect. A dropped tool does not clatter to a table. It simply remains exactly where it was released, drifting only if given a push, following the same orbital path as the astronaut who let it go. Liquids behave strangely as well. Without gravity to pull it downward, water released from a container does not pour. It gathers into a wobbling sphere, held together by its own surface tension, and must be captured with a straw or a specially designed container before it drifts into sensitive equipment. Even the station's ventilation fans take on new importance in this environment. Without gravity-driven convection to circulate warm air upward and cool air downward, exhaled carbon dioxide can quietly collect in a small, invisible pocket around a sleeping crew member's head unless fans continuously push the surrounding air along. Early in the station's history, this was identified as a genuine hazard, addressed by ensuring air handling equipment ran, without exception, in every occupied compartment at all times. Rotating objects behave in ways that have no everyday equivalent on Earth's surface. A spinning wingnut released in midair, filmed by a Russian cosmonaut aboard Mir years earlier, will spin smoothly for several rotations, then abruptly flip end over end, then return to its original spin, repeating the pattern indefinitely. A real effect of rotational physics called the intermediate axis theorem, invisible on the ground only because friction and gravity never allow an object enough uninterrupted time in the air to display it. Physics that had existed the whole time, simply waiting for a place quiet enough to be seen. Every motion has to be relearned. For Shepard, Gitsenko, and Krikalev, that relearning happened immediately and continuously. Walking in the ordinary sense was impossible. Movement through the station's interior meant pulling gently along handrails bolted to nearly every wall, developing within days a kind of practiced controlled drifting that later crews would come to perform almost without thinking. Over the following months, additional missions expanded the station steadily. In February 2001, the American laboratory module Destiny arrived aboard Space Shuttle Atlantis, giving the crew their first dedicated space for scientific research rather than pure life support and habitation. Destiny measured just over 8.5 meters in length and was built with racks along its interior walls designed to hold interchangeable science equipment, furnaces for materials research, freezers for biological samples, and instruments for studying combustion in an environment where flames burn as a slow, nearly spherical glow rather than the flickering, upward-reaching shape gravity produces on Earth. A single large window in its floor, protected by multiple layers of fused silica glass, gave the crew their clearest view yet of the planet passing silently beneath them. The module's environmental systems were also more advanced than anything installed in Zarya or Zvezda, built with finer control over temperature, humidity, and air composition, since many of the experiments it would eventually host required conditions far more stable than the general life support systems elsewhere in the station could guarantee. In its early months, ground teams spent as much time calibrating Destiny's instruments as the crew spent living and working around them. 2 more modules soon followed, each adding a specific new capability rather than simply more space. In July 2001, Space Shuttle Atlantis delivered an airlock named Quest, giving the crew, for the first time, a dedicated chamber for spacewalks that did not require depressurizing an entire module to open a hatch to space. 2 months later, a small Russian docking compartment named Pirs arrived, adding a second port where visiting Soyuz and cargo spacecraft could connect. 2 months later, in April 2001, Space Shuttle Endeavour delivered a robotic arm built by the Canadian Space Agency, formerly named the Space Station Remote Manipulator System, though almost everyone simply called it Canadarm2. Stretching just over 17 meters when fully extended, with 7 independently motorized joints, it was designed to move with a precision measured in fractions of a millimeter, despite handling payloads weighing tens of thousands of kilograms. Unlike the shuttle's own robotic arm, which stayed fixed to a single mounting point, Canadarm2 could release one end, reach across the station's growing structure, and grip a new handhold, walking end over end across the exterior in a motion engineers nicknamed, without much exaggeration, the inchworm. Power and data flowed through the same joints the arm used to grip the structure, so that wherever it attached, it could receive commands and electricity without any separate cable. Over the years that followed, it would be used to capture arriving cargo spacecraft, install entire new modules weighing tens of thousands of kilograms, and even serve as a mobile platform carrying spacewalking astronauts to work sites too far from any fixed handrail to reach on their own. A machine learning to move the way life first learned to move, one grip at a time. By the middle of 2001, less than 3 years after Zarya had launched alone into an empty orbit, the station had grown into a structure with a working laboratory, a functioning robotic arm, a dedicated airlock, a second docking port, and enough electrical power flowing through its new solar wings to support far more ambitious science than its first residents could have run in Zvezda's cramped early days. What it still lacked was any real ability to sustain itself. Every drop of water, every liter of oxygen the crew breathed, still depended on supplies launched from the ground and carried up cargo ship by cargo ship at extraordinary cost. A single Progress cargo capsule, roughly the size of the crew's own Soyuz lifeboat, could carry only so much water and air at a time, and each launch cost tens of millions of dollars before a single kilogram reached orbit. For a station intended to remain occupied indefinitely, importing every breath from a planet 400 kilometers below was never going to be a permanent solution. That dependence was about to change. In a set of systems still being tested, refined, and slowly installed throughout the station's early years, engineers were building machinery capable of doing something no previous spacecraft had ever needed to do for so long, keeping a small, sealed world alive almost entirely on its own, hundreds of kilometers from the nearest breath of fresh air. That system had a name, the Environmental Control and Life Support System, referred to by nearly everyone who worked with it simply as ECLSS. Its job was deceptively simple to describe and extraordinarily difficult to build. Take the air a crew exhales, the water a crew loses through breath and sweat and waste, and turn as much of it as possible back into something breathable and drinkable, without ever running out, without ever failing, and without any technician able to walk in and fix it by hand if something went wrong. The philosophy behind ECLSS traced back decades earlier to far simpler life support systems aboard the Apollo capsules and the American space station Skylab in the 1970s, and to the closed-cycle systems submarine engineers had refined even earlier for crews spending months submerged without surfacing. Each generation of hardware pushed the recovery percentage higher and the required resupply lower, a slow, incremental engineering effort spanning more than half a century before the International Space Station's version reached its current level of efficiency. Air pressure and composition monitoring rounded out the ECLSS portfolio, maintaining cabin conditions closely matched to sea-level Earth air, roughly 78% nitrogen, 21% oxygen, and a small remainder of trace gases, despite the total absence of any natural atmosphere immediately outside the hull. Sensors throughout every module continuously tracked pressure, temperature, humidity, and trace contaminant levels, flagging even small deviations for immediate investigation by both the crew and ground controllers. Trace contaminant control presented its own quiet challenge, since a sealed environment occupied by human beings and their equipment steadily accumulates airborne compounds that would simply disperse outdoors on Earth. Off-gassing from plastics and electronics, trace ammonia from human sweat, and a wide range of volatile organic compounds released by everything from cleaning supplies to the crew's own skin. A dedicated filtration system using activated charcoal and catalytic oxidation continuously scrubbed these compounds from the air, preventing concentrations that might otherwise, over months of accumulation, have grown noticeable or even harmful. The water side of that system carried an official name almost nobody used casually: the Water Recovery System, installed gradually throughout the station's first decade and fully operational by 2009. Its most talked about component was the urine processor assembly, a machine that took a substance most people would instinctively discard and, through a multi-stage distillation process, turned it into water clean enough to drink. Before the water recovery system reached full capacity, urine aboard the station had simply been treated as waste, stored and eventually discarded, along with other trash aboard departing cargo vessels that would burn up harmlessly in the atmosphere. Engineers had understood for decades that recycling it was technically possible. The challenge lay in building a machine reliable enough to run, essentially unsupervised, for years at a time, in microgravity, without the benefit of gravity, to simply let heavier waste settle to the bottom of a tank, the way equivalent systems on Earth take for granted. Yes, that water. The process relied on vacuum distillation, spinning wastewater inside a rotating chamber under low pressure so it would boil and evaporate at a much lower temperature than it would on Earth's surface, since boiling point depends heavily on surrounding pressure. The resulting vapor was then captured, condensed back into liquid, and passed through additional filters and an oxidation process designed to remove any trace of contamination before being blended with other recovered water sources and tested extensively before a single drop reached a crew member's mouth. That testing was not a formality. Every batch of recovered water passed through sensors, checking for dozens of specific contaminants, and samples were periodically returned to Earth aboard cargo capsules for full laboratory analysis, since even a single undetected fault in the system could, in theory, allow something harmful to circulate through the entire crew's drinking supply. Humidity condensate, water vapor collected from the crew's own breath and sweat as it condensed on cooling equipment throughout the station, contributed even more volume to the system than urine did. Combined, these recovery processes allowed the station to reclaim roughly 90% of the water aboard, dramatically reducing how much needed to be launched from Earth in heavy, expensive cargo capsules. In practical terms, the system typically recycled several thousand liters of water a year for a crew of 6, water that would otherwise have required dozens of additional cargo launches over the station's lifetime, each one costing tens of millions of dollars before a single liter reached orbit. Engineers often summarize the system's achievement with a simple, striking comparison. The same water molecules a crew member drank on a given morning might, months earlier, have been someone else's sweat, breath, or waste, cycled through the station's machinery so many times that distinguishing its original source had become functionally meaningless. Oxygen followed a separate but related process, generated by a system called the Oxygen Generation Assembly through a chemical reaction called electrolysis. Electrical current, drawn from the station's solar arrays, split water molecules into their two component parts: oxygen, released into the cabin for the crew to breathe, and hydrogen, which for years was simply vented overboard as waste. A single crew member requires roughly 0.84 kilograms of oxygen per day, a modest figure on its own, but one that adds up quickly across a crew of 6 or 7 people, sustained for months at a time. The oxygen generation assembly could produce enough oxygen for the entire crew using water already recovered by the water recovery system, closing much of the loop between what the crew drank, breathed out, and eventually breathed back in. Backup systems existed for moments when the primary generator required maintenance or repair. Chemical oxygen candles, similar in principle to systems used aboard submarines, could be ignited to release oxygen through a solid fuel reaction, while pressurized oxygen tanks, resupplied periodically by cargo spacecraft, offered a further layer of redundancy in case both other systems failed simultaneously. That waste hydrogen represented a quiet inefficiency engineers eventually solved with a second machine called a Sabatier reactor, installed in 2010. The Sabatier system combined the leftover hydrogen with carbon dioxide exhaled by the crew in a reaction that produced water and methane, recovering water that would otherwise have been lost twice over, first as breath, then as vented gas, and venting only the methane byproduct into space instead. The reaction driving the Sabatier system was not new. First described by French chemist Paul Sabatier more than a century earlier, it had never previously needed to run continuously, automatically, aboard a spacecraft with no chemist present to supervise it. Engineers spent years adapting a reaction first studied in a 19th century laboratory into hardware compact and reliable enough to operate unattended in microgravity for years at a stretch. Nothing wasted if it can possibly be helped. Carbon dioxide removal relied on yet another dedicated system, the carbon dioxide removal assembly, built around beds of a porous mineral called zeolite. Zeolite's molecular structure contains countless microscopic pores that selectively trap carbon dioxide molecules as cabin air is pumped through them, in much the same way a sponge traps water without absorbing the oxygen and nitrogen the crew still needed to breathe. Because the zeolite beds could only hold so much carbon dioxide before becoming saturated, the system operated in alternating cycles, one bed actively scrubbing the cabin air, while a second bed, previously saturated, was heated and exposed to the vacuum outside to release its trapped gas and reset itself for the next cycle. This cycling repeated continuously, day and night, without pause, for the entire duration of the station's crewed history. Each cycle typically lasted a matter of hours, timed by onboard computers monitoring carbon dioxide concentration throughout the cabin in real time. Sensors placed in multiple modules fed data back to the system continuously, allowing it to adjust cycle timing automatically if the crew's activity level and their corresponding carbon dioxide output increased or decreased throughout a given day. Left unmanaged even briefly, carbon dioxide levels aboard the station could climb high enough to cause headaches, fatigue, and impaired judgment among the crew, a genuine operational hazard rather than a background inconvenience, and one ground controllers monitored as closely as any other critical system. The American segment's zeolite-based system was not the only line of defense. The Russian segment operated its own parallel carbon dioxide removal system called Vozduk, using a different regenerable chemical process based on amine compounds rather than zeolite. Running two independently engineered systems side by side, built by two different space programs using two different underlying chemistries, gave the station a level of redundancy that neither program could easily have achieved by relying entirely on its own hardware. As a final layer beneath both of those systems, the station also carried a supply of lithium hydroxide canisters, a simpler, non-regenerable chemical absorbent used as an emergency backup. The same basic technology that had kept the crew of Apollo 13 breathing decades earlier during their own crisis, retained aboard the station specifically for scenarios in which both primary systems failed at once. Temperature control presented an entirely different kind of challenge, one shaped by the extremes of an environment with essentially no atmosphere to moderate it. Facing the sun directly, exterior surfaces of the station could reach roughly 121 degrees Celsius. In shadow, only meters away, the same surfaces could drop to nearly minus 157. Managing that swing required two separate cooling loops working together, described by engineers simply as the internal loop and the external loop. The internal loop circulated water through cabin equipment and around the crew's living spaces, drawing away excess heat generated by machinery, lighting, and the crew members' own bodies, then transferring that heat to a second loop outside the pressurized hull. That external loop carried a different fluid entirely, liquid ammonia, chosen because it remains liquid across an unusually wide range of temperatures and resists freezing even in the station's coldest shadowed periods. Ammonia was selected over water for the external loop, specifically because it could survive the temperature extremes of open space without freezing solid inside the pipes, a fate that would have been catastrophic for a system with no possibility of a same-day repair. Its toxicity made it unsuitable for use anywhere near the crew's breathing air, which was precisely why the design kept the ammonia loop entirely outside the pressurized hull, separated from the crew by the same structural walls that held in the station's atmosphere. The ammonia loop carried absorbed heat out to large radiator panels mounted on the station's exterior, where it radiated away into the surrounding vacuum before circulating back to collect more heat and repeat the cycle continuously around the clock. Two nearly identical cooling loops ran in parallel for redundancy, so that a failure in one would not, in principle, leave the station without any cooling capacity at all. A system built to survive extremes no engineer on the ground would ever personally have to endure. In December of 2013, that external ammonia loop failed in a way that forced an unplanned, urgent response. A valve inside one of two identical pump modules malfunctioned, causing the loop it controlled to overcool and periodically shut itself down as a safety precaution, cutting the station's cooling capacity roughly in half. The malfunction first appeared as a routine anomaly in the data ground controllers reviewed every day, a small fluctuation in temperature readings that within hours grew into something engineers could no longer explain as sensor noise. By the time the loop shut itself down entirely, flight controllers in Houston understood they were looking at a genuine hardware failure, one none of the station's existing spare parts had been specifically designed to address quickly. With one full cooling loop offline, ground teams powered down non-essential systems throughout the station to reduce heat generation, while engineers on the ground worked around the clock to plan a repair that had never been attempted before under these exact circumstances. The solution required physically removing the faulty pump module and replacing it with a spare already stored on the station's exterior, a repair that could only be performed by astronauts in spacesuits, working directly with a system carrying pressurized, toxic ammonia. Even a small amount of ammonia crystallizing on the exterior of a spacesuit during the repair could pose a contamination risk if carried back inside the airlock, so mission planners built an entirely new procedure for the operation, a careful bake-out period in direct sunlight, allowing any stray ammonia particles clinging to the suits to sublimate away into space before the astronauts were permitted to re-enter the station. Over 8 days in December 2013, astronauts Rick Mastracchio and Mike Hopkins conducted 3 spacewalks, disconnecting ammonia lines, removing roughly 780 pounds of failed hardware, and installing the replacement pump module, all while wearing suits with no guarantee that residual ammonia wouldn't vent unpredictably during the disconnection process. Each spacewalk lasted between 5 and 8 hours, conducted in the same extremes of sunlight and shadow described earlier, bright, direct heat giving way every 45 minutes to sudden orbital night and temperatures plunging far below anything most industrial equipment on Earth is ever designed to withstand. By the 3rd spacewalk, the new pump was installed, tested, and brought back online, restoring full cooling capacity to a station that, for more than a week, had been operating on half its designed margin. Mission Control confirmed nominal temperatures within hours, and the crew, some of whom had spent the intervening days in a station running warmer and more cramped than usual, returned to a normal operating rhythm almost immediately. The repair worked, but it stood as a clear reminder that even the station's most fundamental systems, the ones simply keeping temperature, air, and water within survivable limits, depended on hardware that could fail, and on crews trained to fix that hardware themselves with their own hands, hundreds of kilometers from any other source of help. Radiation posed a quieter, less dramatic risk, but one that shaped nearly every design decision on the station's exterior. At 400 kilometers, the station orbits well within Earth's protective magnetosphere, the vast magnetic field generated by the planet's molten core that deflects most charged particles streaming outward from the sun. That shielding is real, but it is not complete. The magnetosphere itself exists because Earth's outer core consists of liquid iron and nickel, churning slowly beneath the mantle in a process that generates electric currents, and with them a magnetic field extending far beyond the planet's visible surface. That field traps many incoming charged particles from the sun before they ever reach low Earth orbit, funneling much of that energy instead toward the poles, where it produces the visible glow of the aurora. From the station's orbit, that same magnetic funneling is sometimes visible directly below, appearing not as a distant curtain of light on the horizon, as it does from the ground, but as a thin glowing ring wrapped around the pole itself, viewed from above rather than from beneath, a perspective almost no human being had ever had the opportunity to witness before this particular structure made it a routine, if still striking, part of certain orbits. Crews aboard the station still receive several times more radiation exposure than people on Earth's surface, largely because the atmosphere above them is thin enough to filter out only a fraction of what a full sea-level atmosphere would block. A 6-month stay aboard the station typically exposes an astronaut to roughly the equivalent of several years of natural background radiation on Earth, a figure closely tracked by radiation dosimeters every crew member wears throughout their mission. That exposure rises further during a specific region of the orbit called the South Atlantic Anomaly, an area over the ocean between South America and Southern Africa, where the inner Van Allen radiation belt dips unusually close to the planet, briefly exposing the station to noticeably higher particle flux each time it passes through. The station crosses this region multiple times a day, spending several minutes within its boundaries on each pass. The anomaly exists because Earth's magnetic field is not perfectly symmetrical, offset slightly from the planet's rotational axis, in a way that causes the field's inner boundary to dip closer to the surface over this particular stretch of ocean than anywhere else on the globe. Astronauts working outside during a pass through the anomaly are advised, when possible, to schedule spacewalk activities around it, and ground controllers track its exact boundaries closely enough to warn crews before each crossing. Sensitive electronics aboard the station occasionally register brief errors, flipped bits of data, momentary computer glitches caused by a single high-energy particle striking a circuit at just the wrong moment, a phenomenon engineers call a single event upset. Astronauts have reported a related, more personal effect: faint flashes of light perceived even with eyes closed, believed to result from high-energy particles passing directly through the tissue of the retina or optic nerve, registering as a brief visual signal despite no actual light being present. Most electronic errors correct themselves automatically or are caught by redundant backup systems, built into the station's design from the very beginning, specifically because engineers understood, decades before launch, that this environment would never be entirely without hazard. Shielded storage areas within the station, positioned deep inside the structure, surrounded by water tanks, equipment, and cargo, also serve as informal radiation shelters, offering crews additional protection during the rare periods when solar activity spikes sharply enough to warrant it. Every safeguard layered on top of another, because nothing here gets a second chance to fail safely on its own. Together, these systems, water recovery, oxygen generation, carbon dioxide removal, thermal regulation, and radiation shielding, did something no single spacecraft before the International Space Station had ever needed to sustain for so long. They kept a small, sealed environment survivable, continuously, for months and eventually years at a stretch, hundreds of kilometers from the nearest replacement part, the nearest doctor, or the nearest breath of unrecycled air. Every one of these systems was built with deliberate redundancy, a design philosophy engineers call fail operational fail safe, meaning the station could suffer one significant failure and continue operating normally, and even a second failure, in most cases, would leave enough backup capacity to keep the crew alive long enough to either repair the fault or evacuate safely aboard a docked Soyuz. That philosophy shaped nearly every choice described so far: 2 cooling loops instead of 1, multiple oxygen sources instead of a single generator, filtration and testing at every stage of the water recovery process, rather than trusting any single safeguard alone. For the crew living inside that redundancy, the machinery rarely announced itself. Most days, the hum of fans, the quiet cycling of the carbon dioxide scrubbers, and the faint mechanical rhythm of the water system simply became background noise, as unremarkable to someone living aboard the station as the hum of a refrigerator is to someone living in an ordinary house on Earth. It was only in moments like the 2013 ammonia failure that the sheer scale of what that background noise was actually doing became impossible to ignore. None of it operated in isolation from the people it kept alive. Every one of these systems existed because a human body, suspended in an environment it had never evolved to survive, required constant deliberate intervention simply to keep functioning, and the environment itself, in turn, was quietly and measurably changing that body in ways engineers could design around, but never entirely undo. The human body evolved over millions of years under a constant, unchanging assumption that gravity would always pull blood, fluid, bone-building stress, and muscular load in one consistent downward direction. Remove that assumption entirely for months at a time, and the body responds by changing, not dramatically or immediately, but measurably, continuously, in ways scientists have tracked closely since the earliest long-duration missions aboard Skylab and Mir. Much of what is known today traces back to Russian cosmonauts who spent months and eventually more than a year at a stretch aboard Mir throughout the 1980s and 1990s, submitting to blood draws, bone scans, and detailed medical monitoring that built the foundational data set later missions would rely on. Valery Polyakov's continuous 437-day stay aboard Mir, beginning in 1994, remains the longest single spaceflight by any human being, and much of what flight surgeons now consider standard knowledge about long-duration physiology originated directly from data gathered during his mission. The most immediate change occurs within hours of reaching orbit, as roughly 2 liters of fluid that gravity normally keeps concentrated in the lower body redistributes upward toward the chest, neck, and head. Faces visibly swell and grow rounder within the first day, a shift so consistent and so rapid that it has become one of the clearest visual signals, even in photographs, that a person is newly arrived rather than long adapted to microgravity. The body's own regulatory systems respond to this redistribution almost immediately, interpreting the sudden surge of fluid toward the head and chest as a sign of excess total fluid volume, since on Earth, that same sensation would only occur if the body genuinely held too much fluid overall. In response, the kidneys increase urine output, and the body reduces its total blood plasma volume by roughly 10 to 15% within the first few days, a genuine physiological miscalculation triggered by an environment the body's ancient regulatory instincts were never designed to interpret correctly. The heart itself changes shape during extended missions, gradually becoming more spherical rather than its usual elongated, tapered form, since it no longer has to work against the same gravitational resistance to pump blood upward through the body that it does on Earth's surface. Cardiologists studying this effect using ultrasound imaging aboard the station found the change measurable within weeks, in most cases reversible within months of returning to Earth's gravity, though the underlying cardiovascular mechanics remain an active area of ongoing research. A body relearning, within hours, an assumption it has held since before birth. That same fluid shift affects the legs in the opposite direction, causing what flight surgeons call puffy face, chicken leg syndrome, a genuine, if informally named, medical description of the way calves and thighs visibly thin as fluid that once pooled there under gravity's pull redistributes elsewhere in the body. The effect is temporary, largely resolving within the first few weeks as the body's fluid regulation systems recalibrate to the new environment. Bone density presents a slower, more serious concern. Bone is living tissue, constantly being broken down and rebuilt by specialized cells, a process regulated in part by the mechanical stress of supporting body weight against gravity. Remove that stress and the balance shifts toward breakdown, with astronauts losing bone mineral density at a rate of roughly 1 to 1.5% per month in weight-bearing bones, such as the hips and lower spine, a pace comparable to, or in some cases faster than, the bone loss experienced by elderly patients with osteoporosis on Earth, compressed into a fraction of the time. The bones most affected are precisely the ones that, on Earth, carry the body's weight during ordinary standing and walking: the hip, the lower spine, and the heel. Bones in the arms and skull, which never bore significant weight-related stress even on the ground, show comparatively little change, a pattern that itself helped confirm mechanical loading rather than some more general effect of spaceflight as the primary driver of the loss. Researchers studying this effect draw on decades of data, tracking bone density before flight, immediately after landing, and at intervals for years afterward, since some portion of lost bone density does not fully rebuild even after a return to Earth's gravity and years of subsequent normal activity. Nutritional intake plays a supporting role alongside exercise in managing this loss. Crews follow carefully calculated diets rich in calcium and vitamin D, monitored closely by flight surgeons throughout each mission, since insufficient intake of either nutrient would compound the mechanical loss already occurring, giving bone rebuilding cells even less raw material to work with during the limited windows when mechanical loading through exercise does occur. Muscle tissue follows a similar pattern, particularly in the large muscles of the legs and back that on Earth work constantly just to keep a person upright. Without that continuous low-level demand, muscle fibers begin to atrophy within days, a measurable loss in strength and mass that, left entirely unaddressed, could leave a crew member barely able to stand upright, let alone walk normally, upon returning to Earth's gravity after a long mission. The soleus muscle in the calf, which on Earth works almost continuously to maintain posture even during ordinary standing, shows some of the most dramatic losses of any muscle group studied, in some cases losing close to a third of its mass during missions lasting several months, a figure that helped convince mission planners early on that exercise could not be treated as optional. Muscle fiber composition itself shifts during extended missions, with a measurable conversion from slow-twitch fibers, optimized for sustained low-intensity effort such as standing and walking, toward faster-twitch fibers better suited to brief, powerful movements. On Earth, this same shift occurs gradually with age and inactivity. Aboard the station, it happens within weeks, a compressed preview of changes that would otherwise take years to develop in a sedentary person on the ground. Engineers and physiologists responded to both problems with dedicated exercise equipment, treated aboard the station not as optional wellness infrastructure, but as mission-critical hardware. The Advanced Resistive Exercise Device, known throughout the station simply as AIRED, used vacuum cylinders rather than traditional weights to simulate resistance, allowing astronauts to perform exercises resembling squats, deadlifts, and heel raises against loads of up to several hundred pounds of resistance, despite there being no actual weight to lift in a weightless environment. Unradan's vacuum cylinders worked by using the pressure differential between two connected chambers, one evacuated and one at normal pressure, to generate resistance as a piston moved between them, an elegant mechanical solution to a problem that on Earth gravity itself solves automatically and invisibly. The device replaced an earlier, simpler resistance machine that flight surgeons determined was not providing sufficient loading to meaningfully slow bone density loss during the station's first several years of continuous habitation. A treadmill, bolted to the wall rather than the floor, required astronauts to strap themselves down with a harness and bungee system, pulling them toward the running surface with a force roughly equivalent to their own body weight, simulating the impact and loading that running on Earth would normally provide. A stationary bicycle rounded out the standard routine, with no handlebars or seat in the traditional sense, simply pedals and a frame anchored to the structure. Roughly 2 hours a day, every day, just to hold the body still against a force that is no longer there to fight. Crews typically spent close to 2.5 hours daily on this combined exercise regimen, a substantial portion of an already carefully scheduled day, reflecting just how aggressively bone and muscle loss needed to be countered to keep a return to Earth's gravity survivable. Even with rigorous exercise, most astronauts still return from long missions measurably weaker than when they left, requiring weeks of rehabilitation on the ground before regaining their pre-flight strength and bone density fully. Upon landing, returning crew members are typically unable to stand unassisted for several minutes, and often longer, as their inner ear and cardiovascular system, both recalibrated to months without gravity's constant pull, struggle to readjust to blood pressure regulation and balance on solid ground. Flight surgeons and support teams are present at every landing, specifically to carry returning astronauts from the capsule, a routine expected part of recovery rather than any indication that something has gone wrong. The immune system shows measurable changes as well, with researchers documenting reduced activity in certain white blood cells, and in a substantial number of astronauts, reactivation of dormant viruses that had lain inactive in their bodies since childhood, including the virus responsible for chickenpox and several strains of herpes virus. Most of these reactivations produced no visible symptoms, detected only through blood and saliva samples analyzed after return to Earth, but they represent a genuine, measurable weakening of the body's defenses during extended time in microgravity. One researchers attribute to a combination of stress, radiation exposure, and the disrupted sleep patterns common throughout long missions. Sleep, too, adapts to an environment the body never evolved to interpret correctly. With 16 sunrises and sunsets cycling past every 24 hours, the station's crew relies entirely on scheduled lighting and strict onboard clocks, rather than any natural cue to regulate their circadian rhythm, since the body's internal clock, tuned over millions of years to a single daily light cycle, has no reliable way to track a day that no longer corresponds to anything happening outside the window. Studies of crew sleep aboard the station have consistently found that astronauts average less sleep than recommended, frequently under 6 hours a night, despite official schedules allotting more, a pattern researchers attribute to a combination of noise from equipment, the excitement and workload of an unusually demanding job, and the simple, disorienting absence of a natural night to signal that a day of scheduled tasks has genuinely ended. Vision presented a subtler, less well-understood risk, one identified only after decades of spaceflight had accumulated enough cases to reveal a pattern. Some astronauts returning from long missions showed swelling of the optic nerve, flattening at the back of the eyeball, and other structural changes collectively named spaceflight-associated neuroocular syndrome, believed to result from the same upward fluid shift that swells the face, this time exerting sustained pressure on tissue behind the eyes over months rather than days. A condition was first widely recognized only in the 2000s, after enough astronauts had independently reported blurred vision during long missions for flight surgeons to recognize a consistent pattern rather than isolated, unrelated complaints. Imaging studies later confirmed physical changes to the shape of the eyeball itself in a substantial proportion of long-duration crew members, findings that reshaped how seriously the space medicine community treated a symptom once assumed to be minor or purely subjective. In response, every long-duration crew member now undergoes regular eye exams throughout their mission, using a specialized ultrasound device small enough to store aboard the station, alongside periodic vision testing using standardized eye charts mounted on a cabin wall. Some astronauts have also worn thigh cuffs designed to temporarily draw fluid back toward the lower body during sleep, an experimental countermeasure intended to partially recreate the downward fluid pull gravity normally provides, tested specifically to see whether it might reduce the pressure changes believed to drive the syndrome. Unlike the fluid shift's more visible effects, these ocular changes do not always fully reverse after return to Earth, and researchers continue actively studying the underlying mechanism, since fully understanding it carries direct implications for how long a human body can safely remain in microgravity before changes to vision become permanent rather than temporary. Radiation exposure, discussed already in terms of the hardware it threatens, carries parallel risks for human tissue, elevating long-term cancer risk in a way flight surgeons track carefully across an astronaut's entire career rather than any single mission. NASA and its partner agencies maintain career-long radiation exposure limits for each astronaut, calculated individually based on age, sex, and cumulative prior exposure, treating the risk as a resource to be budgeted across an entire working lifetime rather than ignored mission to mission. These limits exist because ionizing radiation damages DNA directly, and while the human body possesses natural repair mechanisms capable of correcting most such damage, an elevated cumulative dose statistically raises the likelihood that some damage goes unrepaired or is repaired incorrectly, potentially seeding a cancer that might not manifest for years or decades after the exposure itself. Because women are statistically at somewhat higher lifetime cancer risk from equivalent radiation doses than men, current exposure limits for female astronauts are generally set more conservatively, a policy that has itself been the subject of ongoing scientific and ethical discussion within the space medicine community. Beyond these gradual, well-studied physiological changes, the station's history also includes moments when equipment failure placed a crew member's safety at direct, immediate risk, none more widely documented than a spacewalk conducted on July 16, 2013. Italian astronaut Luca Parmitano was completing routine maintenance work outside the station when he began to notice an unusual sensation at the back of his head, water, cold and unmistakable, pooling against his scalp inside his helmet. Spacesuits circulate air constantly to prevent exactly this kind of moisture buildup, so water accumulating freely inside a sealed helmet indicated a genuine, unexplained malfunction rather than routine condensation. It was Parmitano's second career spacewalk, part of a planned excursion to route cables and perform maintenance tasks alongside fellow astronaut Christopher Cassidy. The spacewalk had been proceeding normally for roughly 40 minutes before the sensation at the back of his head first registered as something other than ordinary sweat. Water inside a sealed helmet 400 kilometers from anywhere it could simply be wiped away. Within minutes, the volume of water had grown enough to begin creeping across Parmitano's face, covering his nose and mouth as he worked to make his way back toward the airlock. In microgravity, water does not run downward and away as it would on Earth. It clings, spreads, and pools according to surface tension alone, meaning a growing volume of water inside a sealed helmet had nowhere reliable to go except directly across an astronaut's breathing passages. Parmitano later described the sensation in his own detailed account of the incident: unable to hear clearly over water covering his ears, unable to speak without water entering his mouth, and unable to see as it crept across his eyes. He found himself relying almost entirely on touch and memory to navigate a structure he could no longer clearly perceive. He described feeling, in his own words, like a fish in a slowly filling bag. Communication problems compounded the danger. Water had begun interfering with the microphone and earpiece inside Parmitano's helmet, garbling his transmissions to mission control, and making it increasingly difficult for either side to clearly describe what was happening or coordinate a response in real time. Parmitano, unable to see clearly, unable to wipe his face inside a sealed helmet, and increasingly unable to communicate normally, relied on memorized handrail positions and a mental map of the station's exterior to navigate back toward the airlock by feel and memory rather than sight. Fellow astronaut Christopher Cassidy, monitoring from inside, worked urgently with ground control to guide him home as the water continued spreading across his face. Inside the station, the crew and ground controllers faced a difficult, entirely unfamiliar judgment call: whether repressurizing the airlock quickly enough to help Parmitano risked its own complications against the clear and growing danger of leaving him outside any longer than absolutely necessary. Mission Control made the decision to prioritize speed, accepting the operational risk of an accelerated repressurization in order to get him out of the suit as quickly as possible. Parmitano reached the airlock and was brought back inside just before the water threatened to fully cover his nose and mouth. A margin later analysis suggested may have been only a matter of minutes before the situation became a genuine risk of drowning inside a sealed suit in vacuum hundreds of kilometers above the nearest body of breathable air. The subsequent investigation traced the failure to a blocked filter inside the suit's cooling and ventilation system, which caused water intended to circulate through cooling tubes to instead leak into the ventilation loop and accumulate inside the helmet. Engineers determined that mineral deposits, likely originating from an earlier, smaller water leak in the same suit during a previous mission, had gradually clogged the filter over time, a slow-building fault that gave no clear warning before finally causing a serious failure during Parmitano's spacewalk. NASA suspended spacewalks using that particular suit design for months, while engineers redesigned the affected components and introduced new safety equipment, including a simple absorbent pad positioned inside the helmet and a snorkel-like tube connected to a separate air supply, giving future astronauts a fallback source of breathable air if water ever again threatened to block their airway. The pad, similar in principle to material found in ordinary household products, was specifically chosen for its ability to wick water away from an astronaut's nose and mouth, even in the total absence of gravity, to help it drain. The incident prompted a broader review of suit maintenance procedures across the entire fleet, including more rigorous post-flight inspection protocols intended to catch exactly the kind of slow, undramatic mineral buildup that had gone unnoticed until it very nearly caused a fatality. Parmitano himself returned to complete additional spacewalks in later missions, and the suit design changes introduced in the aftermath remained in active use throughout the station's subsequent history. A margin of minutes and an engineering fix that followed almost immediately. The incident, along with the ammonia pump failure described earlier, reflects a broader pattern in the station's history. A structure built with careful layered redundancy nonetheless depends, at critical moments, on individual human judgment, memorized procedure, and split-second decisions made by people wearing suits that are themselves small, self-contained, and imperfect spacecraft. No amount of engineering fully removes the fact that every person who has ever worked outside the station has done so wrapped in equipment that could, in the wrong combination of failures, become dangerous within minutes. Despite these risks, no fatality has ever occurred aboard the International Space Station itself, a record maintained across more than a quarter century of continuous human presence, hundreds of individual astronauts, and thousands of cumulative hours spent working outside its pressurized hull. That record reflects not the absence of danger, but the accumulated effect of exactly the kind of redundant systems, rigorous training, and rapid engineering response described across both this section and the last. Every astronaut who launches toward the station today trains for months specifically on failure scenarios like Parmitanos, practicing in pools and simulators on the ground, exactly the kind of blind, memory-guided navigation he was forced to perform in real conditions, so that if water or any other unexpected hazard ever again threatens a spacewalk, the response is no longer improvised under pressure, but rehearsed calmly and repeatedly long before it is ever actually needed. That accumulated caution, layered year after year on top of the last, is itself a kind of quiet, ongoing achievement, an outpost built by and for a species not naturally suited to the environment it now occupies, almost without interruption, still learning one incident and one engineering fix at a time exactly how to belong there safely. Not every hour aboard the station was spent fighting the effects of the environment. A significant portion of the crew's time was spent studying it directly, running experiments that simply could not be performed anywhere gravity was present to interfere. By the station's third decade in orbit, researchers from more than 100 countries had flown experiments aboard it, spanning fields as varied as materials science, fluid physics, fundamental particle physics, and plant biology, a research output substantial enough that the station's laboratory modules had, by then, hosted more individual scientific investigations than any single facility in the history of spaceflight. Protein crystal growth became one of the station's most consistently valuable areas of research. On Earth, gravity causes growing crystals to settle and distort under their own weight as they form, producing structures too irregular for scientists to study in fine detail. In microgravity, with nothing pulling the growing crystal toward any particular surface, proteins can form larger, more symmetrical, more precisely ordered structures than any laboratory on Earth can reliably produce. Researchers used these station-grown crystals to study the exact three-dimensional shape of proteins linked to diseases including muscular dystrophy and certain cancers, since understanding a protein's precise structure is often the first step toward designing a medication capable of interacting with it effectively. Pharmaceutical companies and university laboratories alike have flown experiments to the station specifically for this purpose, treating the microgravity environment less as a novelty and more as a genuinely useful laboratory tool unavailable anywhere else. One widely cited example involved a protein linked to Duchenne muscular dystrophy, a severe muscle wasting disease primarily affecting children. Crystals grown aboard the station revealed structural detail sharp enough to help researchers understand precisely how a candidate drug molecule interacted with the protein's surface, detail that Earth-grown crystals, distorted by their own weight during formation, had never been able to provide clearly enough to work from. Similar station-grown crystal studies have contributed to research on treatments for certain forms of cancer, examining proteins involved in tumor growth with a level of structural clarity ground-based laboratories have struggled to match. Several pharmaceutical companies have flown repeat missions specifically to refine crystal growth conditions for their own proprietary drug candidates, treating access to microgravity less as a scientific curiosity and more as a competitive advantage worth the substantial cost of a dedicated cargo launch. A quieter kind of discovery, built one crystal lattice at a time. Combustion research offered a similarly unique opportunity. On Earth, a flame's teardrop shape exists because hot air rises, drawing in fresh oxygen from below and creating the familiar flickering, upward-reaching form. In microgravity, with no upward convection to shape it, a flame instead burns as a slow, nearly spherical glow, spreading oxygen and fuel toward itself through diffusion alone rather than any directional air current. These microgravity flames burn cooler and more efficiently than their earthbound counterparts, sometimes continuing to burn even after appearing, to a camera, to have gone out entirely, a genuine safety consideration for spacecraft designers, and a source of genuinely new combustion physics, inaccessible anywhere gravity pulls hot air away from a flame's base. Data gathered from these experiments has informed the design of more efficient, cleaner burning engines back on Earth, an unexpected practical return from research that began purely as an effort to understand fire in an unfamiliar environment. One long-running series of combustion experiments, conducted inside a specialized sealed chamber aboard the station, studied cool flames, a faint, nearly invisible combustion state that exists briefly during the ignition of certain fuel droplets, burning at temperatures low enough that a human hand could, in principle, tolerate brief contact with one. On Earth, cool flames extinguish within a fraction of a second, too quickly for detailed study. In microgravity, without buoyant convection to disrupt them, researchers recorded them persisting for minutes at a time, long enough to gather data no ground-based laboratory had ever been able to capture. Not every experiment aboard the station studied the station's own environment. In 2011, Space Shuttle Endeavour delivered a particle physics detector called the Alpha Magnetic Spectrometer, a 7-ton instrument mounted permanently on the station's exterior truss, designed to catch and analyze cosmic rays, high-energy particles streaming through space, many originating from sources well beyond the solar system entirely. The instrument's installation was itself a notable engineering achievement, requiring astronauts to use Canadarm2 to lift and precisely position a detector roughly the size of a small car onto a specific truss segment, aligning delicate sensor arrays to tolerances of a few millimeters, despite the entire operation being conducted by remote manipulation from inside the station's cabin. Built around a powerful magnet that bends the path of each incoming particle, the detector measures that curvature to determine the particle's charge, mass, and energy, cataloging billions of individual cosmic ray events since its installation in a continuous search for antimatter and evidence of the unseen mass astronomers called dark matter. Unlike ground-based detectors, which must contend with Earth's atmosphere absorbing or altering incoming particles before they arrive, the station's orbital position gives the instrument direct, unfiltered access to cosmic rays, exactly as they exist in open space. The detector's data has not yet delivered the single, unambiguous discovery some physicists initially hoped for, but it has produced by far the largest and most precise catalog of cosmic ray particles ever assembled. A resource physicist on the ground continued to mine for subtler patterns years after any individual measurement was first recorded. The instrument's power and cooling systems were designed for a planned operational life of several years, yet it has continued gathering data for well over a decade beyond that original estimate, outliving its own design specifications in much the same way the station hosting it has outlived several of its own original engineering timelines. Plant growth experiments carried both scientific and practical significance. A facility named Veggie, installed aboard the station in 2014, allowed crews to grow red romaine lettuce, Mizuna mustard greens, and other crops using LED lighting tuned to wavelengths plants use most efficiently for photosynthesis, and specially designed pillows that delivered water and nutrients directly to the root system without gravity to help the process along in the way soil-based watering normally relies on. Without gravity to provide a consistent directional cue, plant roots aboard the station initially struggled to reliably determine which direction to grow, since root growth on Earth relies partly on sensing the pull of gravity itself, a mechanism called gravitropism. Engineers compensated by using the pillow's internal structure and carefully directed lighting to guide root growth mechanically, giving the plants an artificial substitute for the directional cue gravity normally provides for free. Later experiments expanded well beyond lettuce and mustard greens. Crews successfully grew radishes, chili peppers, and even a small crop of wheat, each new species requiring its own adjustments to lighting, watering, and nutrient delivery, gradually building a body of practical horticultural knowledge with direct relevance to any future mission attempting to grow food far beyond Earth's supply chain entirely. In August 2015, the station's crew became the first humans to eat food grown and harvested entirely aboard a spacecraft, sampling their own station-grown lettuce after months of testing to confirm the crop was free of harmful bacteria. Beyond nutrition, researchers viewed the experiment as an early, essential step toward any future mission that might need to grow food during years-long journeys, too distant to be resupplied from Earth at all. The first bite of a plant that had never touched soil. Fiber optic manufacturing represented one of the station's more commercially promising research areas. Certain specialty glass fibers, when manufactured on Earth, develop microscopic crystalline defects as gravity causes their molten material to settle unevenly while cooling, defects that degrade the fiber's ability to transmit light signals efficiently over long distances. Manufactured in microgravity instead, these same fibers form with dramatically fewer defects, potentially transmitting data with far less signal loss than anything producible on the ground. The specific material involved, a heavy metal fluoride glass known as Zeblan, has been studied on Earth for decades as a theoretically superior alternative to standard silica fiber optics, promising signal loss reduced by up to 100-fold over long distances. On the ground, gravity-driven crystallization during manufacturing has always prevented Zeblan from reaching that theoretical potential in practice, a limitation researchers hoped microgravity manufacturing might finally overcome. Early production runs conducted aboard the station returned fiber samples that outside laboratories confirmed to be measurably clearer than any Zeblan ever produced on Earth. Though manufacturing volumes remained small, limited by the size of the equipment that could realistically be flown to orbit and operated inside the station's existing modules. Scaling that process into genuine commercial quantities remains an open engineering challenge, one several companies continue actively pursuing. Private companies began flying dedicated fiber manufacturing hardware to the station specifically to explore this advantage commercially, one of several signs by the station's third decade in orbit that its usefulness had grown to include not just government-funded science, but genuine industrial application run by private companies paying for access to microgravity the same way a factory might pay for any other specialized manufacturing condition unavailable elsewhere. Between experiments and around the structured demands of exercise and maintenance, crew members found their own quiet observation of the planet becoming, for many, one of the most meaningful parts of daily life aboard the station, a fact confirmed repeatedly enough in post-mission interviews and journals that psychologists studying long-duration spaceflight began treating it as a genuine, measurable component of crew well-being rather than simple sentiment. In 2010, that observation gained a dedicated space of its own, a module called the Cupola, a dome-shaped observatory fitted with 7 windows, including one of the largest ever flown on a crewed spacecraft, was installed on the station's Earth-facing side, giving crews an unobstructed, panoramic view of the planet passing beneath them for the first time in the station's history. The cupola's central window measured roughly 80 centimeters across, framed by 6 smaller trapezoidal windows arranged around it, together forming a dome that allowed a crew member floating inside to see almost the entire hemisphere of sky and planet below simultaneously, rather than through the narrow single-direction view any earlier window on the station had offered. Each pane consisted of multiple layers of fused silica and borosilicate glass, thick enough to protect against micrometeoroid impacts, while still remaining optically clear enough for detailed photography. In, out. Before the cupola, windows aboard the station had been small, scattered, and often positioned more for engineering convenience than for observation. The cupola changed that entirely, becoming almost immediately the most popular unscheduled destination aboard the entire structure, a place crew members gravitated toward during rare free moments, simply to look down. Photographs taken from the cupola have since become some of the most widely circulated images the station has ever produced, used in scientific studies of storm systems, coastal erosion, and city light patterns, alongside their more straightforward role as some of the most visually striking documentation of Earth ever captured by a handheld camera. Canadian astronaut Chris Hadfield, commanding the station in early 2013, became one of the first crew members to share this view widely and directly with a global audience, posting photographs from the cupola to social media throughout his mission, and in doing so, introducing millions of people outside the space program to a perspective previously described mostly in official mission reports and scientific papers, rather than shared in something close to real time. His photographs of specific cities, deserts, and coastlines, often paired with brief, plainly worded captions identifying what viewers were looking at, reached an audience many times larger than any single piece of station-related media that had come before it. From that vantage point, a single orbit takes 93 minutes, meaning a crew member watching continuously would see the sun rise and set 16 times in a single 24-hour period, each sunrise and sunset compressed into a matter of seconds, rather than the slow, extended process familiar from a lifetime spent on the ground. During each of these transitions, the thin band of Earth's atmosphere becomes visible edge-on as a fragile, glowing line separating the planet from the blackness beyond it, a boundary encompassing every layer of breathable air the entire species has ever depended on, visible all at once, from outside it, as something startlingly thin. That line typically appears as a narrow gradient of deep blue fading into black, spanning a region of the atmosphere only a few hundred kilometers thick relative to a planet with a diameter of nearly 13,000 kilometers, proportionally thinner, by some comparisons, than the skin of an apple relative to the fruit inside it. Astronauts have described this particular view, the atmosphere rendered suddenly as a fragile finite line rather than an invisible unlimited given, as one of the most quietly affecting sights available anywhere aboard the station, a moment where a familiar scientific fact about atmospheric thickness becomes briefly something closer to a direct physical realization. A boundary the whole of human history has lived beneath, seen all at once from outside it. City lights at night reveal patterns invisible during daylight passes, the dense branching glow of major population centers, the comparatively dark stretches of ocean and desert, and, during periods of heightened solar activity, the shifting green and violet curtains of aurora, viewed from above rather than below, wrapped in a slow, silent ring around one of the planet's poles. Fishing fleets, working at night with bright lights specifically to attract their catch toward the surface, create some of the more surprising patterns visible from orbit, forming distinct, densely clustered points of light across otherwise dark stretches of open ocean, dense enough in some well-known fishing grounds to be mistaken, at a glance, for a coastal city rather than a scattered fleet of individual boats. Lightning storms, visible from orbit as brief, silent flashes rippling beneath cloud cover, occur somewhere on Earth almost constantly, a fact astronauts have confirmed simply by watching, without needing any instrument, across nearly every extended pass over a populated hemisphere. From 400 kilometers up, an entire storm system structure becomes visible in a single glance, a scale of observation no ground-based vantage point could ever offer. In, aim, out. Much of this photography was not purely personal. A NASA program called Crew Earth Observations formally tasked astronauts with photographing specific locations requested by scientists on the ground, ranging from retreating glaciers and shrinking lakes to active volcanic eruptions and changing coastlines, building a continuous, decades-long photographic record used by climate researchers, geologists, and disaster response teams alike. Because the station's orbit carries it over nearly the entire populated world on a repeating cycle, and because a trained human eye can often recognize a subtle, significant change in terrain or ice cover that an automated satellite camera might pass over without flagging, crew photography has, on multiple occasions, provided the first documentation of specific environmental events later confirmed and studied in greater detail by dedicated Earth observation satellites. The overall effect of this sustained, repeated view, a planet without visible borders, its weather systems and city lights and fragile atmospheric edge, all rendered continuously visible from a single, unbroken vantage point, has been widely described by astronauts as a shift in perspective that persists well beyond the mission itself, sometimes summarized informally as the overview effect, a term coined by writer Frank White after interviewing astronauts about the experience in the early 1980s. White's original research, conducted before the International Space Station itself existed, drew on interviews with astronauts from earlier programs who consistently described a similar shift regardless of their nationality, political background, or the specific mission that had carried them into orbit. A consistency that led White and later researchers to treat the effect as a genuine, reproducible psychological response to a specific visual stimulus, rather than a coincidence of personality or prior belief. Whatever name is given to it, the underlying observation is a simple factual one. From 400 kilometers up, national borders so consequential and so carefully defended at ground level are entirely invisible, and the atmosphere sustaining every living thing on the planet appears, from that distance, as a boundary thinner than the edge of a coin held at arm's length. Subsequent researchers studying long-duration spaceflight have documented measurable, if modest, shifts in some astronauts' self-reported values and priorities following extended missions, particularly regarding environmental concern and a broadened sense of connection to people outside their own country, findings consistent enough across multiple independent studies to be treated as a genuine area of ongoing psychological research rather than simple anecdote. The station's slow, continuous drift over the planet below offered its crews something rare, even among the small number of people who have ever left Earth's surface at all. Enough time and enough repetition for a view most human beings experience only once, if ever, to become instead a quiet, ordinary part of an otherwise carefully scheduled working day. Even after months aboard, crew members have described the view as never quite becoming routine in the way other aspects of station life eventually did. The exercise equipment, the food preparation, the maintenance checklists, all of which settled over time into unremarkable habit. The Earth outside the window, by nearly every account, never fully made that same transition into background noise. Some astronauts have described developing an almost involuntary habit of checking the window during any unscheduled moment, a handful of seconds between tasks, spent simply confirming what continent or ocean happened to be passing beneath the station at that particular point in its orbit. A small, repeated ritual that persisted, largely unchanged, across missions lasting anywhere from a few weeks to more than a year. By the time a typical 6-month expedition ended, a crew member would have completed close to 3,000 individual orbits of the planet, witnessed something close to 48,000 individual sunrises and sunsets, and photographed, in many cases, hundreds of thousands of individual frames of the world turning steadily beneath them. A body of observation larger in raw volume than nearly any single human being in history had ever personally recorded of the planet they called home. Ground teams, meanwhile, continued the quieter work of keeping all of this possible, monitoring the life support systems described earlier, tracking the station's slow orbital decay, and scheduling the next reboost, and preparing always for whatever the following rotation of crew, cargo, and experiments would require next. The station's rhythm, unlike almost anything on the ground below it, had no true pause, no holiday, and no night, only the same 16 sunrises, repeating every single day for years that had already stretched, by then well past anyone's original expectations. Every structure built to circle the Earth carries, from the moment of its first launch, an ending already written into its design. The International Space Station is no exception, and its ending, unlike much of its history, has already been planned in considerable detail. By the early 2020s, the station's oldest modules, Zarya and Zvezda among them, had been in continuous operation for well over 2 decades, far longer than either had originally been designed to last. Engineers conducted repeated structural assessments throughout this period, examining metal fatigue, micrometeoroid damage, and the slow wear of components never intended to remain in use this long, extending the station's certified operational lifetime again and again as each new assessment confirmed the structure remained sound. Every square meter of the station's exterior has by now absorbed the impact of countless micrometeoroids and small fragments of orbital debris, too tiny to track individually from the ground, each impact leaving a microscopic pit in the outer hull. Engineers monitor the cumulative effect of these impacts closely, since even particles smaller than a grain of sand, traveling at orbital velocities of several kilometers per second, carry enough kinetic energy to slowly erode protective coatings and, in rare cases, damage sensitive equipment mounted on the exterior. Larger debris receives a different kind of attention entirely. Ground-based radar tracks tens of thousands of objects larger than about 10 centimeters currently orbiting the Earth, and whenever one of these objects is projected to pass close enough to threaten the station, flight controllers can command a small engine burn to shift the station's orbit slightly, avoiding the object entirely rather than relying on the structure's shielding alone. These collision avoidance maneuvers have become a routine, if still carefully calculated, part of the station's operational life, occurring several times in a typical year. Metal fatigue in particular required careful ongoing study, since the station's hull flexes almost imperceptibly with every temperature swing between direct sunlight and orbital shadow, a cycle repeating 16 times a day, every day for more than 2 decades by the time these later assessments were conducted. Engineers modeled this cumulative stress using data gathered continuously since the earliest modules launched, comparing predicted wear against actual inspection results gathered during spacewalks and robotic arm surveys of the exterior structure. NASA and its international partners have set a target date of 2030 for ending the station's operational life, with a planned deorbit occurring sometime in 2031, a controlled, deliberate departure rather than an uncontrolled, unpredictable one. In 2024, NASA selected SpaceX to build a dedicated spacecraft for this purpose, a vehicle informally called the U.S. Deorbit Vehicle, designed specifically to guide the station's final descent. That vehicle will be substantially larger and more powerful than any cargo spacecraft the station has used before, since guiding a structure with a mass exceeding 400,000 kilograms safely out of orbit requires far more thrust than routine reboosts or cargo deliveries have ever demanded. An ending already scheduled for a story that is, for now, still being written. Unlike the gradual altitude loss described earlier in this story, the slow, routine drag countered every few weeks by small engine burns, a deorbit is deliberate and irreversible. The deorbit vehicle will dock with the station and at a precisely calculated moment fire its engines in a sustained burn designed to lower the station's orbit decisively, aiming its eventual atmospheric entry at a specific, carefully chosen point on Earth's surface, rather than allowing it to fall unpredictably. As the station descends into progressively thicker atmosphere, friction against air molecules moving past its structure at several kilometers per second will generate heat intense enough to ionize the surrounding air itself, wrapping the falling structure in a glowing sheath of plasma, similar in principle to the fireball visible around any spacecraft returning from orbit, only vastly larger in scale. Aluminum, the primary material used throughout most of the station's hull, melts at a temperature the re-entry heat will exceed within seconds, causing the majority of the structure to break apart and vaporize during descent. Not every component shares that fate equally. Denser parts built from materials with higher melting points, certain structural joints, portions of the truss, and elements of the propulsion systems are expected to survive re-entry's extreme heat long enough to reach the ocean's surface largely intact, following trajectories engineers can predict closely enough based on decades of data from previous spacecraft re-entries to ensure they land within the planned target zone near Point Nemo rather than scattering unpredictably across a wider area. Engineers refer to this final controlled descent as a targeted re-entry, a technique refined over decades of deorbiting progressively larger spacecraft, beginning with early satellites and cargo vehicles, and culminating in stations like Mir and eventually the International Space Station itself. Each previous targeted re-entry has provided additional real-world data on exactly how different materials, shapes, and structural configurations behave under the extreme heat and deceleration of atmospheric entry, refining the predictive models engineers will ultimately rely on for the station's own final descent. Skylab, America's earlier and much smaller space station, offers a cautionary counterexample from 1979, when a failed targeting attempt scattered debris across a sparsely populated region of Western Australia rather than the intended ocean target, a widely publicized outcome that directly shaped the far more conservative, carefully calculated approach engineers now apply to any large spacecraft's final descent. The Australian town nearest the scattered debris later fined the United States $400 for littering, a fine that went unpaid for more than 3 decades until a radio host raised the funds and personally delivered payment in 2009, a small, almost lighthearted footnote to an event that nonetheless left a lasting, serious impression on the engineers responsible for planning every large spacecraft re-entry that followed. That point already has a name, though most people have never heard it: Point Nemo, located in the South Pacific Ocean, roughly equidistant from the nearest 3 landmasses in any direction, named after the fictional submarine captain from Jules Verne's novels, whose own name meant no one in Latin. Point Nemo sits so far from any coastline that the nearest human beings, at certain times, are not on any nearby ship or shore, but aboard the International Space Station itself, passing overhead in orbit. The nearest inhabited land to Point Nemo lies more than 2,600 kilometers away in any direction, a distance greater than the separation between many entire countries, across open ocean rarely crossed by shipping lanes, and almost never visited except by the occasional research vessel studying the region's unusually sparse marine ecosystem. Its remoteness is precisely why space agencies chose it. Any surviving debris falling into these waters poses effectively no risk to human life, ship traffic, or populated coastline. That same remoteness makes the surrounding water among the least biologically productive stretches of ocean on the planet, since it sits far from the nutrient-rich currents that support marine life closer to continental coastlines. Oceanographers sometimes describe the region as more comparable, in terms of biological activity, to a desert than to the rest of the world's oceans, a further coincidental reason it was judged an acceptable location for decades of accumulated spacecraft debris. For decades, space agencies have used the waters surrounding Point Nemo as an unofficial spacecraft graveyard, a deliberately chosen deorbit target for retired satellites, cargo vehicles, and space stations too large to fully burn up during atmospheric re-entry. More than 200 spacecraft, by some estimates, already rest on the seafloor in this remote stretch of ocean, including Mir, the Russian station whose decades of accumulated experience had helped make the International Space Station itself possible in the first place, deliberately deorbited into these same waters in March 2001. When the International Space Station eventually follows that same path, the largest pieces, likely including portions of Zarya and Zvezda, the very first modules described at the beginning of this story, are expected to survive re-entry's extreme heat long enough to reach the ocean surface largely intact. joining Mir and the rest of that quiet, deliberate collection resting in some of the most isolated water on the planet. That ending remains years away. Between now and then, the station's role has already begun shifting, gradually, toward a different kind of future. Private companies have begun developing their own commercial space stations, intended eventually to take over many of the research and habitation functions the International Space Station has performed for more than 2 decades, operating not as a government-run scientific outpost, but as a commercially leased facility available to any customer willing to pay for access. Several of these projects have already progressed well beyond early planning. Axiom Space, a company founded by former NASA officials, has been developing modules originally intended to attach directly to the International Space Station before eventually detaching to form an independent commercial outpost of their own. Other companies have proposed entirely separate stations, built from scratch and launched independently, each competing to be ready before the International Space Station's own operational life comes to its planned end. None of these commercial successors yet carries the accumulated operational history the International Space Station holds, the specific knowledge of exactly how its particular ammonia loops behave under exactly this station's specific thermal cycling, exactly how its particular hull has weathered exactly 25 years of micrometeoroid impacts. Each new station, however carefully designed, will have to rebuild at least some of that experience from its own first years of operation, in much the same way the International Space Station itself once had to. This shift did not emerge suddenly. Commercial cargo missions had already been resupplying the station for more than a decade by the early 2020s, and commercial crew missions carrying astronauts to and from orbit aboard privately built and operated spacecraft had similarly become routine well before any serious plan for a commercial station existed. Each step normalized the idea that private companies could reliably handle tasks once considered the exclusive responsibility of government space agencies. NASA's own strategy explicitly anticipates this transition, describing a future in which the agency purchases services and research time aboard privately owned and operated stations, rather than owning and operating the hardware directly, much as it now purchases seats aboard commercially built spacecraft to reach orbit in the first place. Several companies have already begun early construction and testing of modules intended for these future commercial outposts, aiming to have working alternatives available before the International Space Station's own operational life comes to its planned end. The reasoning behind this shift is largely economic. Operating the International Space Station costs the United States alone several billion dollars annually, a sum government space agencies increasingly hope to redirect toward deep space exploration, missions to the Moon, and eventually Mars, while leaving routine low Earth orbit research and habitation to companies for whom it represents a primary business rather than one small part of a much larger exploration program. Much of what makes those future deep space missions possible traces directly back to lessons learned aboard this station. The life support systems described earlier in this story, refined over decades of continuous operation, now inform the design of Gateway, a smaller station planned for orbit around the Moon as part of NASA's Artemis program, intended as a waypoint for future lunar and eventually Martian missions. Engineers working on Gateway have explicitly cited the International Space Station's ECLSS systems, its redundancy philosophy, and its accumulated data on human physiology and microgravity as a direct foundation for that next generation of hardware. Gateway will orbit the Moon rather than the Earth, following a distant, elongated path that brings it as close as roughly 3,000 kilometers from the lunar surface at times, and as far as nearly 70,000 kilometers at others. An environment far harsher in some respects than the International Space Station has ever had to withstand, with far weaker protection from both radiation and micrometeoroid impacts than Earth's own magnetosphere provides at 400 kilometers up. Every lesson the International Space Station has taught engineers about redundancy, about failure response, and about keeping a small crew alive far from any possibility of quick rescue applies there with even greater consequence. Where the International Space Station can, in a genuine emergency, return its crew to Earth's surface within hours aboard a docked Soyuz or commercial crew capsule, a crew stationed at Gateway would face a return journey measured in days rather than hours, placing far greater weight on exactly the kind of redundant, self-sufficient systems this station spent 25 years refining. In that sense, every failure endured and repaired aboard the International Space Station, the ammonia pump, the flooded helmet, the countless smaller malfunctions never widely reported, has quietly lowered the risk for whoever eventually lives and works that much farther from home. In this sense, the station's ending is not simply a conclusion, but a handoff. 25 years of accumulated engineering knowledge, medical data, and hard-won operational experience, much of it earned through exactly the kinds of failures and repairs described across this story, passed forward into whatever comes next, whether in low Earth orbit, around the moon, or eventually farther still. Until that transition is complete, the original station continues exactly as it has for more than 25 years, crewed without interruption by rotating expeditions arriving every few months, running experiments, conducting maintenance, and passing overhead 16 times a day at nearly 8 kilometers every second, 400 kilometers above a planet whose entire history of powered flight fits comfortably within a single human lifetime. That comparison is worth sitting with briefly. The first sustained controlled airplane flight occurred in 1903, covering a distance shorter than the wingspan of many modern commercial aircraft. Less than a century later, human beings were assembling a structure the size of a football field in orbit, using robotic arms and international cooperation, and keeping people alive there continuously for years at a stretch, an arc of technological change compressed into a span of time some living people can still, in principle, remember beginning to end. Between those 2 points, a wooden aircraft skimming a few meters above a beach in North Carolina, and a 400,000 kilogram structure circling the planet every 93 minutes, lies the entire recorded history of powered human flight. No other stretch of comparable technological transformation in human history has been witnessed, start to finish, within a single lifetime quite so completely. It is worth pausing briefly on the scale of that continuity. Since November 2nd, 2000, the day William Shepard, Yuri Gudzenko, and Sergei Krikalev first floated through the station's hatch, human beings have occupied this structure without a single full day's gap, through economic crises, changes in government on every side of the partnership, a global pandemic that grounded most air travel on Earth, and every other disruption the last quarter century has brought to life on the ground below. More than 280 individual expeditions have rotated through the station across that same period, carrying astronauts from more than 20 different countries, each arriving as a newcomer to an environment no amount of ground-based training can fully replicate, and each departing months later, having personally experienced the fluid shifts, the bone density changes, the exercise regimens, and the 16 daily sunrise described throughout this story. Among them, teachers, military test pilots, physicians, engineers, and, in later years, private citizens flying as part of commercially arranged missions, each contributing their own small addition to a body of medical and scientific data that now spans a quarter-century of continuous human presence in orbit, data no single mission, however carefully designed, could ever have produced alone. Some of that data has already outlived the astronauts who provided it, informing medical protocols for radiation exposure, bone density monitoring, and vision screening that now extend well beyond the space program itself into terrestrial medicine's own understanding of how the human body responds to prolonged immobility, altered fluid balance, and extended isolation, knowledge with direct relevance to bedridden patients, aging populations, and anyone else whose body, for whatever reason, spends extended periods without the ordinary mechanical stress gravity otherwise provides for free. Somewhere, at this exact moment, a crew is aboard it, sleeping or exercising or floating quietly near a window, watching a sunrise that will last only a matter of seconds before giving way again to night. Ground teams on 3 continents continue their own quiet half of this same routine, monitoring telemetry, calculating the next reboost, and preparing cargo manifests for the next resupply mission, much as their predecessors did in the winter of 1998, when the entire station consisted of nothing more than 2 unlit, unoccupied cylinders drifting in the dark. In and out. Slowly, that structure continues its work. Water recycled, oxygen generated. A body slowly losing bone density and slowly rebuilding it in the careful balance engineers spent decades learning to maintain. A view of the planet repeated nearly 16 times a day that has never by any account become entirely ordinary to the people who hold it. 16 sunrises, 16 sunsets. Ammonia circulating quietly through lines outside the hull, carrying heat away into the dark. Zeolite beds cycling, filters turning wastewater back into something clean. A crew somewhere inside, breathing air that has been breathed before by other crews in other years, recycled and returned again and again for more than a quarter of a century. None of it stops. None of it has stopped, not once, since the 2nd of November in the year 2000. The station that began as 2 empty cylinders, bolted together by hand in the vacuum of space, grew, piece by piece, mission by mission, into the largest and most complex structure human beings have ever built beyond the surface of their own planet. It has outlasted every original schedule set for it, weathered failures in its most fundamental systems, and carried, across more than 280 individual expeditions, people from more than 20 different countries who arrived for a time as strangers to microgravity and left months later, changed by it in ways science is still working to fully understand. From a 15-meter pair of unlit modules drifting alone above the Earth in December of 1998, to a fully crewed, football field-sized laboratory conducting research in medicine, physics, and agriculture, the station's growth traces, almost point for point, the same 25 years this story has followed, from Zarya's lonely first orbit to the crowded, humming structure it eventually became. One day, not too many years from now, its final pieces will settle quietly into the deep, remote water near Point Nemo, alongside Mir and everything else already resting there. Until that day arrives, it remains exactly what it has been since November of 2000, occupied continuously by human beings 400 kilometers above the ground. Everything you heard tonight is real. The International Space Station is out there right now. If tonight's story helped you drift off, a like, a subscribe, and turning on notifications helps this channel keep telling stories like it. Sleep well.